investigate exponential functions, okay? Because exponential functions and logarithms are inverses of one another. You guys remember back to the beginning of chapter 3 and chapter 2, we talked about inverses? Okay? Functions that pass the horizontal line test have inverses, correct? Well, every exponential function that we come across is going to pass the horizontal line test, so it has a inverse. Every exponential inverse is a logarithm, okay? So we'll talk about these things as we move through this section. But I just want to give you kind of a visual of what exponentials look like y equals 2 to the x, okay? If I write it that way, this 2 here is referred to as your base, okay? They're called exponential functions because that's where you find the variable. It shows up in the exponent, okay? But exponential functions, if you see, they rise pretty quickly, right? Okay? You hear people say something has increased exponentially, right? You've heard that phrasing, okay? Well, that's why they say it. It's because that's what that exponential graph does. It rises very, very quickly. It gets to very, very large y values in a very, very short period in regards to the x values. But this value here, this 2, is referred to as your base. I'm just going to write it as a right now. It's kind of boring when a is 1. Okay, it's not an exponential anymore when a is 1, because what's 1 raised to the first power? 1. What's 1 raised to the third power? What's 1 raised to 100th power? 1. So you get basically 1 every time, right? So a better way of writing y equals 1 to the x is just call it y equals 1, right? So horizontal line. So we have if you go back to the PowerPoint, we have the restriction when we define an exponential function. It says the exponential function with base a is defined by all real numbers x by which f of x equals a to the x. A is greater than 0, okay? And a cannot be 1, okay? A could be a half, it could be a fraction between 0 and 1, but it can't be 0 and it can't be 1. If it's 1, it's boring, okay? And you see that if a is negative, we have some issues, right? It disappears. And we'll talk about why eventually. So let me take this slider real quick and let's make it go to 1 to 10, talk about increments of 1. I just want to put a key point on here. Let's put point right there. And you watch that ordered pair as I change the function, as I change the base. What happened to that ordered pair? Absolutely nothing, right? So that tells me, and we're only seeing like 9 different exponentials there, right? But that might be enough to realize that 0, 1 is on every exponential function we talk about, okay? Before we move it left, right, up, and down. But 0, 1, think about this. 2 raised to the 0 power. What's anything raised to the 0? 1. So if my base is 100, 100 raised to 0 is 1, okay? So you're always going to have 0, 1, okay? I'm going to put another point on here. Now, this one's going to change a little bit, but you should be able to see how it changes. I put that point B on there, okay? And I start changing that A value. It's now at 1, 2. It now goes to, oh, B needs to go with it. Attach B to there. Shut up. There we go. So if I'm at 2, I got the point 1, 2, right? Because 2 raised to the first power is 2, right? X being the exponent, so 2 to the first is 2. Well, 3 to the first should be what? 3. So look at that order pair, 1, 3, right? So if I go x to be 1 again, but now it's maybe 4 to the x, I would get 1, 4, right? So we're seeing then that B value, that ordered pair at B is always 1, whatever your base is, right? And we're calling, a lot of times we call the base A, okay? 3 to point 1, A. You see over there on the whiteboard, I've got some ordered pairs already up there, right? Okay, those are 3 ordered pairs that are useful for every exponential function, okay? 0, 1, 1 comma A being your base. Okay? But I got another one here, and we're going to go back to probably algebra 2 maybe, to use our understanding of why this one shows up the way it is. If I have, let's say, 2 to the x, but x is -1. Okay, so that gives me 2 to the -1, right? Do we ever like to have negative exponents? No, so the way we deal with negative exponents is to do what with that 2 to the -1? Yeah, it goes to the denominator, right? So it becomes 2 to the first and the bottom. Now nothing's left over, so I'm left with what on top? 1. What's that value right there? Does that make sense, everybody? So 1/2 and 2 are what types of numbers to one another? Reciprocals. If I take A and make it 3, what is the y value there? 1/3, right? If A is 4, what's the y value there? 1/4. If it's 5, it's 1/5. Okay? So we're seeing that no matter what A is, okay? So if this function here is f of x is equal to a to the x, that point right there is always 1 comma A. That point right there is always 0 comma 1. And that point right there is always -1, the reciprocal of A, so 1 over A. Okay? And that's going to be very, very useful for us in regards to graphing eventually logarithms. Logarithms are a pain in the butt to graph, but if we know that they're inverses of one another, okay, just real quick show you, if I know that these are inverse of one another, let's take, what are inverses, the reflection across what line? Y equals x, right? So I'll draw on the line y equals x. When they're inverses, basically the ordered pairs just flip-flop. So if I reflect this function across that line right there, that curve in the the fourth and first quadrant is a logarithmic function. Does that make sense? Okay. So that's why it's going to be important for us to really grasp the understanding of how to graph exponentials. Tomorrow we'll start talking about how, what if I add numbers to x and add numbers to the entire thing? Where does that take that exponential? Yes, sir.